1.6, graphs of functions. We'll start with example, graph f of x equals x squared minus 6. So if we don't know how to graph a function, we can always make a table, and we select values for x that are easy to compute. Let's start with 0, which will give me -6, 1 will be -5, and negative values as well. -1 squared is 1, -6, -5, 2, -2, -2 would also give -2, and so on. Let's plot these points and pick a scale. So this is -6, 0, -6. The other point is 1, -5, and -1, -5, and 2, -2, and -2, -2, and we can do 3. 3 squared, 9 minus 6 is 3, and -3 will give me the same value. So let's see, for 2, okay. So 3, -3 is somewhere here. I can connect this, and we have a parabola. Another example will involve a piecewise function. So let's graph f of x equals 4 minus x squared if x is less than 1, and x minus 3 if x is greater or equal than 1. So we graph this piecewise function by first graphing the first branch. So y equals 4 minus x squared is going to be a parabola that opens down. In fact, I can do this right away. 1, 2, 3, 4. So it opens down, but we need to graph it for x less than 1. So we could make a table. If x equals 1, that point is not going to be included. That's going to give me 3, but I'm going to have here a hole. It's going to be a whole point. If x equals 2, that gives me 0. -2 gives me 0, 3, and that's too much. I think that's enough. So we're plotting the first point, 1, 3, right here. It's a hole. And then let's see, 2, 0. That point we don't need because we need less than 1. So -2, 0 right here. And if x is 0, that's the point I needed to do. If x is 0, we get 4. So that's the point here. Here's the parabola, or part of it. The other part is a line. So for y equals x minus 3, can make a table as well for values of x greater or equal than 1. So let's do 1, gives me -2, 2, -1, 3, 0, and so on. So 1, -2 is this point, and then 2, -1 is here, and 3, 0. So a line going this way, this point is included. And this is our piecewise function. A definition that we use when we talk about functions is the concept of a zero. C is a zero of f of x if f of c is equal to 0. So 0 is the input that makes the output 0. So c also becomes an x-intercept. So the 0c of f is the solution of f of x equals 0. So c is also solution of the equation f of x equals 0. Symmetry. Symmetry of graphs. So what we call even function is a function that satisfies this equation f of negative x is equal to f of x, and that is true for every x. The graph of an even function has symmetry with respect to the y-axis. So symmetry with respect to the y-axis. Odd function satisfies the equation f of negative x is negative f of x, and we have symmetry with respect to the origin. So a couple examples to clarify this. F of x equals x squared, our quadratic function. Looks like this, parabola with the vertex of the origin, and we see the symmetry with respect to the y-axis. So this is even. An example for odd would be x to the third. The graph is symmetrical with respect to the origin. Okay, so this is odd. Some more examples for functions that we only know the equation. Even, odd, or neither. Even, odd, or neither. A, f of x equals to 5 over 2 minus x squared. So we're checking what's happening to the function if we plug in negative x. So we put negative x in parentheses, and we have to do square first, order of operations, so that becomes 2 minus x squared. Be careful not to cancel those two negative signs because you have to square first. So negative squared is positive. So we get the same expression as f of x. So we say this is even. B, g of x equals 5x over 2 minus x squared. Plug in negative x. We have 5 times negative x over 2 minus negative x squared, negative 5x over 2 minus x squared. Well, that's exactly the opposite of g of x. So this function is odd. C, h of x equals 5x over 2 minus x to the third. Plug in negative x. 5 times negative x over 2 minus negative x to the third, negative 5x over 2 minus x to the third. Now we compare, this is g of x, and this is what we got. I'm sorry, I meant to put this one. Compare these two. Okay, so we compare these two, and we see that this one is neither even nor odd. So it's not the same and it's not the opposite. All right, so anything else about functions? We talked about domain, range, increasing and decreasing. So general function behavior, we're going to sketch a graph that changes its behavior. And it looks something like this. I'm going to label the first point where we start -4, -3. The first high point here, -2, 4.5. and the lower point here is 3, -8. This point, 4, -6. This point is 5, -6. And the last point is 6, 5.5. So we have labeled all the key points in the graph, and now we're going to answer several questions. First, domain. The domain of the function. Then we're going to talk about range, increasing, decreasing, constant, if there is any interval where the function is constant, local minimum, local maximum, absolute minimum, and absolute maximum. So let's start with the domain. So our function starts with -4 and ends with 6. So we're looking at the x values. The range, we're looking at the y values from the bottom to the top. And the lowest point is -8, including. The highest point is 5.5. Okay. Increasing. So where's the function increasing? That means it goes up and to the right. Seems like it's increasing from -4 to -2. We're listing the x values for the interval. Let's just make this red. So this is increasing. And it's also increasing here. And it's also increasing here. So 3 intervals. We're going to describe them. From -4 to -2, the first one. Then from 3 to 4. And then from 5 to 6. So these are the intervals of increasing. The decreasing, there are 2 intervals of decreasing. Falling down, again we're describing the x values from left to right. So that would be from -2 to 3. And that's it. Only this interval is decreasing because the other interval is constant. So it's constant from 4 to 5. Local minimum. This is the lowest point in a neighborhood. I see the local minimum at 3, -8. Okay. And that's it. A local max, -2, 4.5. Absolute minimum. So the absolute lowest point is the same as the local minimum, so it's the same. Absolute means for the entire interval, for the entire domain, this is the absolute minimum. The absolute maximum ends up being that endpoint 6, 5.5. So the absolute minimum and maximum can be at the endpoints, but the local minimum and maximum has to be inside point, inside the interval, not an endpoint. And that concludes the 1.6 section.